Hello, 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 hello.
So they're picking out tablets that give the I guess the way this thing is.
Oh, so I should join in Zoom or whatever.
Right on Indian government. In the
Yeah. But the MAC address and all that is not required.
Right. It is the top rank university. It's the top rank.
Yeah.
We're not giving layers.
Yeah. So my like sharing data that's making so I didn't know I think lazy. So what I can do, I can
I think you come to Dipankar once. If it's just that's what I thought.
They have scratched that. I can take so I know this is exactly.
So if I can use yeah. So you pay.
Then of course, yeah, it was a problem. Usually, where we have to reach
Attending the workshop, no, that's my career is very but but it was the workshop, right? So that company is right, you attend those. And both are on the same page. I mean, from yeah, I think that after all the Colosseum, I just
audio share for this.
No, I understand. Yeah, it's actually black on set of No, I don't think we should take the issues here at this point in time. Let me have a chat. They have a chat. It's correct at this point in time. It's correct. I'll talk to Dipankar and get back.
Is this,
I know.
this, Twitter, I
I saw that you didn't know.
No, it's actually.
The evening, by 5:30 should be done, I think by 5:30. Okay, sounds good. Shut up. Thank you.
Yes, sir. Actually, starting out the composition.
পুরো সবগুলো স্পেশাল ফিল্টার
ভালো ছিল।
তাদেরকে ঢুকিয়ে দাও না, হল
বলবেন অসুবিধা নেই আমাকে একটু দিয়ে দেবেন
মাঝখানে কিছু চেয়ার বাইরে পাওয়ার এখান থেকে মাইক্রোফোন
Very good afternoon, all of you. This Bose Colloquium lecture. And we are very happy to have Professor Dipankar Banerjee. Your mic is not delivered this Bose Colloquium lecture. And I request our director, Professor Shishada, to kindly introduce.
Thank you, Rajiv. Good afternoon, everyone, and warm welcome to today's Bose Colloquium, which will be given by Professor Dipankar Banerjee, who is known as a very renowned solar physicist. I was actually searching your Wikipedia. Solar physicist. I really like that word. And he is currently the director of ARIES, which is another sister institute of AST, and he is also the senior professor at IIA, Indian Institute of Astrophysics in Bangalore. And Dipankar is very much a person from this city because he completed his bachelor's degree at St. Mary's College, Calcutta, and he had his PhD from IIA under the supervision of Professor S.S. Asar. And after that, he worked as a postdoctoral fellow in Almag Observatory and on specifically working on solar atmospheric dynamics, which is his area of specialization. And this was followed by a Flanders Fellowship at Catholic University of Leuven in Belgium, and that made his Belgian connection very strong. And in 2004, he returned back to India and also back to IIA and became the director of ARIES in 2019. And his primary research interest, as I already mentioned, is study of dynamics, solar atmosphere. He has many recognitions, but I think in today's context, the two worth mentioning is he was the co-PI for the near UV imaging instrument on the Aditya L1 mission, and he was co-chair of the science working group for the Aditya L1 mission. So today's talk, I think, will be a story that we'll listen from horse's mouth, and we have also already seen some trailer of that, whatever he is going to present, and I'm pretty sure it is going to be very exciting. And you can already see the enthusiasm. It's a packed hall, and we have another hall even where it is being streamed. So without wasting any more time, I welcome Dipankar to the
Thank you very much, Shri, for your introduction and very generous introduction. It's always been a pleasure for me to be back in this city of joy. I was born and brought up here in early part of my career, and the rest of the time mostly spending in Bangalore and in recent years in Nainital. This named colloquium is again, I think, makes me nervous. Bose is a name which is there in the Bengali heart and culture, and this institute is also carrying that legacy. And the multidisciplinary nature of this institute is also really worth mentioning. So it's just not the boson. So now we are having new avatars in terms of our space missions. So today, my task is to give you some flavor of this mission called Aditya L1. So before I go into the mission concept, probably being a solar physicist, as you mentioned, But I don't know who made that Wikipedia page. These days, you suddenly discover that you have some description somewhere. I have not created that page. So, but people do find out from different sources, I guess. So if somebody points out some mistakes, yeah, there's another Dipankar Banerjee
Yes.
in IIC, and often I get a very good, Google Scholar profile if people do not split them. So it's a very common name in this part of the country. So now, on a serious note, this mission involves really a large number of people all across the country, different institutions, different laboratories, different parts of ISRO centers, at different phases of its mission also. Because at different phase, different kind of skill sets and people get involved. And now we have to a stage where thing is delivered, but our work starts almost now, to be honest, to create really the credibility of the community that we are able to do something what we have promised to do. So I am again putting up a lot of logos of these institutions just to represent to you that it is really, really large collaboration, and I'm just on behalf of the science working group present here. So I have to click on this first. Move on. So the sun, our nearest star, shows different kind of variability. Often you see in the solar atmosphere such dynamic, very fast, phenomena. This is a eruption what you see from a region of the sun, as seen from some coronal emission lines. This is the image taken from Solar Dynamic Observatory of NASA, which shows that sun is brighter as compared to the other part of the sun. And traditionally, these brighter regions have been named as active regions. And now we also know that underneath these active regions, there is a strong presence of magnetic field. Magnetic field is the form of sunspots, and these sunspots have been observed almost 400 years now after the discovery of the telescopes. But now these are our, ideal laboratory because you can actually study a lot of different branches of physics in this nearest star, the sun, and particularly these magnetic objects really, really provide you a lot of, avenues for doing plasma physics, atomic physics, molecular physics, and all that. So I won't go into details. Normally when I interact with the students, I try to emphasize that you are interested in particle physics, please come and start solar physics. If you're interested in nuclear physics, please come and study solar physics. So you name any physics, I can connect with the sun. So that will be some other day. But then my point is that these regions are known to be very dynamic. They're changing. It's not so easy to predict their dynamics in advance. Active regions do give big, huge impacts on our interplanetary space in the form of space weather. You will find thankfully a good colleague of mine, younger colleague is there, so I will find some slides which I borrowed from you in the past also, because he is the magnetic field guy. So, so these are the sunspots which I am talking about, and what is shown here is location of the sunspots, and they are always bipolar, as you see here from the black and white nature of this. And whether there will be a sunspot at some day or will be absent in 1 month down the line is also not very easily predictable. There is some trend, what we see. I got this from Amazon just a few days back. I'm looking at that direction, so that's very good. Going in the wrong direction. Okay, so it's my mistake, not your madam. So the sunspots are now believed to be coming because of these kind of flux tubes. They float because they're lighter than the surroundings, and when they come out of the surface, they form this kind of pairs of sunspots. But you see the behavior of these, magnetic structures. When you twist and make certain rotations and all that, you saw at certain point that whatever material which was confined within this plasma, they were ejected out. So that gives rise to this ejecta, and this phenomena is also called the flares, which takes into this, variability what you see in the atmosphere and its effect. Now there is another part of variability which is long term. So these short term variability which I was showing in terms of the magnetic instabilities and so on, here what you see is what is plotted here is 400 years of records of sunspots as recorded from ground-based telescopes. You clearly see alternate peaks in solar activity. When there are lots of sunspots, we call it maxima. When there are hardly any sunspots, we call it minima. This is predominantly cyclic with a periodicity of 11 years. This is a period when Samuel Swabe observed that, and just note, just looking at this behavior, he said that there is a solar cycle of 11 years. So that's the kind of people had the ability to predict something which was proven much later on. What is the effect? This is a more recent space-based, output of the solar irradiance. So that is the luminosity of the star, considered to be constant in all astrophysical contexts, but in our solar and the climatic context, we know it is not constant. It does vary with the 11-year periodicity as well. So this is what is plotted red is the sunspot number, and this is the total solar luminosity, are called irradiance. But mind it, this is total solar flux integrating over all wavelengths. Now we understand that they may not be true, or the variability may not be so little at 0.01% in all wavelengths. And that is why one of the instruments which is there on our mission is going to probe that or prove that whether it is the case. So the total solar irradiance coupled the sun's magnetic output. So basic point is it's a magnetic field, and its variability is crucially dictating what is going to be the future of the sun in terms of minutes, hours, days, or months, or millennia. So to understand the magnetic variability is the key. For that, of course, you need magnetic observations. There are limitations of these magnetic observations. And we will also say, our mission, what is the progress we can doing that. This is again a most recent output from a group of people who has tried to attempt to predict the solar cycle, how the solar cycle will be in the next, say, 10 years or so. So this prediction happened sometime around this year. There was a big consortium. I think Dipankar was also part of that consortium.
No, I was still part of it.
You were not in the Hathaway.
They're doing it wrong.
So I just wanted to point it out that how raw this field is. Of course, they are still claiming, I've taken from David Hathaway's Facebook page. He has given this that way, because as you see, this is the prediction. Few months back, what has happened was the things were showing these fluctuations. But if you take the average, now they are clearly things are coming back also. So of course, this is a very, very controversial subject area. But point is, predicting the magnetic behavior of the sun in all time scales is the crucial question what we have to understand. For that, we have to understand why the magnetic field is there in the first place and how it is going to evolve with time in a day's time scale or hours time scales and years time scale. So the physics is slightly different when you pose a different question. This is typically, again, a data taken from Solar Dynamic Observatory. These are called active regions. And here you see there was magnetic instability. And incidentally, I didn't plot the size of the Earth. The size of the Earth will be something like this. So you can imagine how much material is confined in this huge structure. And then when this huge structure is throwing away all this material into the planetary space, some material again fall back. That also has a lot of other implications. You see, some material is hot, some material is probably cold. So there is a lot of plasma diagnostics which you need to do also to understand this. So that was a zoom portion of a portion of the sun. Now, if you look at the full disk, then you see how big these structures are. But then to follow up these structures to the interplanetary space, you need an instrument called a coronagraph. That is what is shown here. You have blocked the solar disk, and you have followed actually that ejecta all the way from sun to a very large distance away. So that's a coronagraph which is there on the SOHO spacecraft, which is also incidentally in SOHO at Lagrangian point. This is another coronagraph which is called C3 coronagraph, which is looking at even beyond, several solar radii. There is also a stereo spacecraft and all that, which gives you a perspective from a different vantage point as well. So stereo is an identical twin satellite, which is looking at the sun from two vantage points and trying to do stereoscopy. So there is actually, why I'm showing a bit of these things is that a lot of development which has already happened in the global scenario. So we have to fit in our mission into something which is still missing in our understanding. There's also a new attempt to go much closer to the sun. This is a result from Parker Solar Probe. Parker is traveling more towards the sun. They're going so close to the sun they can't even look at the sun. They're looking away from the sun. As you can see, these are called, again, certain imagers, but not looking, taking images on the solar disk, but taking images on the heliosphere. And when such ejecta comes, how they travel and their trajectory and all that is important to predict again the impact when these objects will be in our nearest environment. Because in our nearer environment, we are filled with a lot of space assets, satellites and so on, and it is important to save those space assets. I see the chairman often is emphasizing the fact that this mission has costed 400 crores, but we have 5,000 crores worth of satellites in space. So now these missions are going to help in our understanding about the space weather effects and mitigation plans for future time. Here I'm again showing as these ejecta comes out of the sun, and it reaches in the earth, these are stitched from different instruments, again from stereo spacecraft. The stereo spacecraft is not only looking at from two vantage points, it has a combination of imager and coronagraph and a heliospheric image. So essentially that is allowing for the first time to track as this object comes out and what time it can take, what is the structure of these magnetic objects. And I will also say these objects are called coronal mass ejections, and no two CNEs are the same. We have looked at almost 10,000 CNEs by now, so almost no two CNEs are the same. But you have to understand the behavior. Sometimes you do have to classify certain events into one basket. So you have to have many different baskets, and then only you can do the prediction or characterization of the propagation of these CNEs. So now when this ejecta comes in, of course, here we are in the cocoon of the magnetic field of the Earth. Thankfully, otherwise we would not have existed. And here there are another interesting aspect which is happening in the solar physics. We don't call it anymore solar physics. We call it heliophysics, because sun and the other planets, all inclusive, we have to study the behavior. Dipankar does a lot of other planet interaction as well.
So you should be called
Heliophysicist. If I get the access to the editing,
I should remember.
but it is all happening step by step. The other interesting thing you mentioned, see, Earth's magnetospheric physicists, when I was doing PhD, there was not a single interaction between the Earth's magnetic, magnetospheric physicist and a solar physicist. We know anything happens in that magnetosphere, disturbances or changes, is because of the sun. So unless you understand the sun's variability, you cannot, understand the impact. So the source has to be understood to understand the impact. But where is the gap? The magnetospheric physicists solve the plasma equations in the kinetic domain. We solve the equation in the MXG domain. So magnetohydrodynamics is again a simplification of the plasma physics with a single fluid disk. But again, we have to talk to each other. We have to match these two models. Again, the still evolutions are happening. There is one called big code, one is called the MXD code, and how do you match this? So even theoretically, I tell you, there are a lot of differences, but we have to talk to each other, work with each other to have a comprehensive understanding of the source and the effect. So this is because unless you do not, again, I'm repeating, unless you understand the source region and the ejecta which is traveling, its properties in terms of its temperature, plasma, its composition, everything is required. So that's why I'm showing a lot of images today, just to make things look very attractive, but the physics happens when you have spectroscopy, where you have ability to do, plasma diagnostics, because physics will be only complete when you have all the physical parameters inside, not the just one velocity component of it. So just, I'm not again going into the details, but there are so many different regions in the Earth's, magnetosphere, and all these phenomena is crucially dependent on what is coming from the sun. There is a continuous expansion of the solar outer atmosphere in the form of solar wind, which is there. On the top of that, you have the CMEs. So it's like, you have a river flowing with certain water, and then I throw a stone. So depending on the flow of the water, the stone's, trajectory will be decided. So there is a drag also when this, this particular stone is thrown into the water. So you have to understand the flow of the water. You have to understand the property of the stone, which here is it a stone or it is a plasma blob. When it's a stone, it's actually life is much simpler, but unfortunately it is not. It's a plasma blob, which doesn't have a regular shape or size. So life is complicated, but progress has to be made by a comprehensive understanding. This is again Dipendu's group work. Here they are modeling this impact of solar wind and the storms on the Earth. So these kind of models, I'm happy to see that we are making progress in this kind of modeling. Actually, in India, it wasn't there 10 years back, definitely. So because these demand a lot of computational resources, but also demands how to simplify things and do a computer modeling. Because if you are limited with some resources, you have to be always smart enough to find out alternative ways of looking at the problem. So I'm glad, so this kind of work is happening here. So this is a really new field which has emerged in the space era, which is called the space weather, because we are so much dependent on the on the communications and the different layers of the atmosphere, primarily the ionospheres, and so on. And there are all these depictions. I will not again go into the details, but as you can very well understand, all our satellite communications, GPS coordinates, if we are planning to make some space tourism, of course, the one good thing about our sites is now the rich people actually can afford this. And the rich guys like Mr. X is really spending a lot of money into this kind of research. And that helps in our showing the importance, because whenever they lose something, it's out of a billion. In fact, he did lose 40 of the satellites. Very simple. He didn't. He ignored the solar physicists because there was a small little storm. It was not a very big storm, but the storm did not impact any of the satellite which was launched those days. But the interplanetary environment changed. So the drag force which were necessary to be calculated for the trajectory of these, low Earth orbit satellites, none of them could reach those, particular heights. So that way he lost. I understand. I think Aditya was also working with his student to do some further conclusion why does such a disaster happen. So thankfully, hopefully, Mr. X will give us some fun to next time, before he launches the satellite. So telecommunications, air traffic, the astronaut safety. Of course, for Western world, there is another few other important areas like the power grids and oil pipelines and so on. Thankfully, again, we are being in India in the low latitudes and so on. We don't get affected that much because all these energetic particles and ejectors tries to enter to the polar regions, and any high latitude countries they get affected, and it did happen many a times in near past as well. This is again a favorite slide of the wind, which I like very much, particularly for explaining to physicists that, see, this is again a part of the heliosphere thing. When you are looking at interior of the sun, the study or the surface and so on, then you are in an environment where plasma beta is much more than 1. So plasma beta basically dictates whether it is the velocity field that the plasma flows are dominating over the magnetic field. So it appears that the magnetic field for the interior, although they are strong, but the velocity field is much, much stronger. and the majority of the dynamics is governed by more of the flows rather than the field. But there are transitions when we are going into the corona, then everything is controlled by the field. So if you can study the field and its behavior, you will know that automatically the fluid is carried with the field. So of course we can't directly see the field, we only see the material. So the assumption is that the flux is frozen with the material, and if you can track the material, then in a way you are actually tracking the magnetic field as well. Having said that, this is also missing till today, that we do not have ways of measuring the magnetic field in the corona. So this is one of the, again, a very important element which we are trying with the Aditya mission to get an estimate about the plasma, the magnetic field in the corona. And then I will again have to give a little history about the mission now. So let me take you to your mission pipeline or mission timeline. What you see here is generally the solar cycle. We started talking about a solar mission way earlier, as early as 2006. It coincided very well with my return to back home. And at RRI, we started discussing about a space mission. And incidentally, this was driven by a vision document which was prepared by the Academy of Sciences, G. Srinivasan. He was also the president of ASI at that point of time. So that's the other reason we are now giving a very big importance to the mission document of ASI, which is under preparation and will be announced very soon. We were given to build a coronagraph, rather IIA was built to given this responsibility, imaging coronagraph for a low Earth orbit mission around 2009. Money was given, we were started designing and things like that. But then something happened around this 2013 time scale. Mangalyaan was a successful mission. Professor U.R. Rao got the head of the advisory committee of space, and he sort of called some of us, and then I think Dipankar was also with us in that small little afternoon discussion. He said, "Would you like to go to Lagrange?" We actually, frankly speaking, I couldn't believe that somebody from India is talking about going to Lagrange. We were only expecting a small mission, taking one payload of. Of course, we immediately said yes, but then we can't take the same instrument. We need, I mean, we scientists are always, over ambitious and also a bit greedy. So, so the opportunities were given to the entire nation. Different institutions submitted proposals, and 7 payloads were selected. That took a while, and then, of course, different individual institutions started building this. But we had COVID challenge, which coincided with the solar minima, as you can see here. And then, thankfully, payloads were all delivered early 2023 this year, and we got our launch on 2nd September. So I must say this is quite an amazing thing which is happening in India. I mean, I know I can tell you, typically when you hand over a space payload, and the launch is 1.5 years to 2 years time difference in any space agency, as advanced as NASA itself. So I don't know how ISRO is managing. Of course, it's probably much bigger manpower, but I think it has to be commended with their style of functioning as well. I don't think with such precision, because it is so challenging to have all these missions with no failure kind of options. The ground-based telescope, I now see, every other day there is some problem, we have the option of going back and fixing it. But in space, just that doesn't exist. So I think it's quite commendable, and we are fortunate to be there this time. This is a sequence of things which happened on that day. Of course, this happened before, 2 days before, as the payloads were transferred to Sriharikota. There are lots of people in the outside with the 40 degrees of temperature outside. It took quite a while because there were different phases, and the separation happened about 1 hour down the line. Here, this is the takeoff, and I remember when I was sitting close inside, and they said that they want to hear this boom as it comes out, but I did not leave my seat inside. No, I have a little superstitious in terms of watching cricket, that you shouldn't leave your seat. If you change your positions, next ball you don't know what is happening. So they enjoyed the boom going out in the seeing the balcony, but I was all inside. But it was a lifetime experience, and I can't believe that I could witness to such an experience. And when you know that such babies are being carried with this boom outside every stage, there is a bit of tension, and you hope for the best. So thankfully, I think this is quite amazing. There are so many steps, where things can go wrong, but I think they have redundancies for every step. That's why they're so successful now. So that's the separation sequence what you'll see. I will not spend too much time on explaining different Lagrange points. I do it with another operation, but I think you are more familiar with that. So we are only going to L1. Other astronomy missions are there at L2. I will briefly talk about our own trajectories and so on. We took a slightly, probably poorer map, poor man's, route. Rather than going directly, we took several Earth-centered orbit transfer route. This was normally taken now for long-distance flights. 5, to be precise. Second, we were launching, and then 22nd September we left the Earth-centered orbit. This was the cruise race, and then
Dipankar, sorry to interrupt you.
Sure.
Why is this route followed in all ISRO's missions, like the lunar mission? And if you compare it with other countries' mission, like the Soviet Union, of course it crashed in. But why do you follow such a, as you say,
it is the engine. It just means how much kick you can give. So they have more powerful engines, and it is more expensive.
So ISRO has so far not been able to develop such form.
They don't want to. They are happy with this. So if it is necessary to go even further, they may develop that skill. But what I understand, it's just a sort of they're more happy with this kind of model. How to?
I mean, I could not resist myself. I don't know how many of you have seen this movie where Bita Balan was in the main character. She was saying precisely explaining what is the advantage.
That's Sita, in fact,
Yes,
So
exactly.
I don't know whether the audience people know that's Sita's life,
That's it.
which is there depicted by Aditya L1. So after this maneuver, we were actually taking in this route. I will talk about it. That's what I was indicating to Pedu in the other day message, what it really happens. One thing to be noted here is it's a halo orbit, not in one plane. So here I could manage to get the simulation from the ESA people because there are 3 other missions, SOHO AS, which is there in the wind in the Lagrange, orbit. And as you can see from this, simulations, they are not in the same plane. So essentially, we have to do the balance of the forces between the satellite and the Earth and the satellite and the sun. It has to supply the centripetal force which is required for a orbit, halo orbit, at all point of time. So, okay, I also that time I was showing this on 10th, first time the aspects, one of the particle detector payload, got some signal as that. All the way before the insertion, actually, time to time, there have been all instruments been turned on, and there's some tests has happened, which shows very promising. Apart from the coronagraph, which is much more tricky, I will show why. Most of the other instruments have been sort of been tested already. This is what actually finally ISRO has put up in their website. What was happening, last few weeks was we were taking this route. So this route is actually 1/4 of a part of the halo. So that's why, suit and all that was operational. And this is not too much. I mean, this is again exaggerated because of the drawing. This is not too much different from these orbital path. That's why they were so confident. And we were allowed to turn on the instruments as well. So what has happened is that day, I think 31 meters per second or something was given a boost, not to take up this dash line, but to get into this pink line. And that only happened for even half a minute, I was told. So they were doing very well. So already they were in pretty good shape. But that really allows them to, even if you have missed this, apparently there were redundancies that you can see. Again, some fuel would have been utilized to get back to this particular orbit. And this exercise will be probably required once in maybe 3 to 6 months. Because as you can see here, this is again shown in one plane, but it is not in one plane. So they will be monitoring how things are. So there could be small little deviations, and then the thrusters may be huge. But depending on how often we have to use the thrusters and all that, our life at around Lagrange will be dictated. Okay, so I have the movie. Sorry. There are some movies which these people made. So this is
studies the solar corona and dynamic coronal oxygen. The Solar Ultraviolet Imaging Telescope, SUID.
okay. So essentially, so what we're talking about. Yeah. Now it means we are talking about a combination of we are at L1, a combination of remote sensing and in situ instruments. I will talk about that now. There is this solar ultraviolet imaging telescope, the coronagraph, and the two X-ray spectrometers, Helios and Solex. One is looking at the high energy flares, one is looking at the low energy flares. These are looking sun as a star. We do not have an X-ray imaging yet. This is again a new thing. X-ray imaging doesn't it's still infancy in India. We have particle detectors to probe the properties of these particles which are coming, whether it is hydrogen, helium, or protons, or with different charge ions. What is the charge to mass ratio? Whether they're carrying magnetic field or not. For that, the magnetometer is also there. So it is a multi-payload observatory class mission. It has to be kept in mind. It has multi-wavelength coverage. It's a combination of 4 remote sensing and 3 teams. So it really caters to a large community of expertise. But again, we have to now work together to get a full comprehensive idea. So it is an observatory class mission. And then somebody was asking me, what is my role at the mission now? We are really trying to highlight how important it is to use the multi-wavelength capability. For astrosat also people try. I think there was some success, but I think for solar physics, there is no other alternative now apart from doing multi-wavelength astronomy. It has a capability of address many scientific problems. I will not be able to discuss that. It needs probably one full day. This is just highlighting the portion of the wavelength which we are covering. Incidentally, PELC, the coronagraph, is looking at the higher ionic transitions of iron in optical. This is typically been observed during the total solar eclipses, and that also has certain properties of polarization or spectropolarimetry. With that, we will be trying to get a sense of the magnetic field in the corona for the first time. Solar ultraviolet is going to look at these 200 to 400 nanometer region, and incidentally, there is no such continuous observation available in these wavelengths from space platform. There have been rocket and there have been balloon experiments, but no near UV images in space. So this is going to be definitely the first time as well. So let's, as I indicated, is going to look at low energy. The other contemporary emissions, we're looking up to 3 keV. We are going even lower, up to 1 keV. I was told up to 0.5, they're able to get a signal with the significant power. So the complete list with ability of 3 visible and 1 infrared channel is led by IIA here. The SUIT instrument is led by Ayuka, which you have also heard in the movie. These are the 2 particle detectors led by TRL and Space Physics Laboratory from Thiruvananthapuram. The 2 X-ray spectrometers are at different ISRO labs, primarily at URSC, and the magnetometer is also another lab at LEOS in Bangalore again. So a lot of institutional involvement is there. I will just highlight few areas where things are missing in terms of the observation which is available. This is one area as far as heavy observation is concerned. This is taken from LASCO C2, and this is a full disk imager from Solar Dynamic Observatory. Both are this is SOHO mission, this is NASA mission. This area, regular observation is not there. We have sporadic ground-based observations. So where this exactly the CME is coming out, the source region again is not well understood. And the initial phase of the acceleration of the CME is also something missing. So what we are doing is we are focusing on exactly that. Yellow circle is our imaging field of view, and we have additionally these multi-slit experiments. So this is the first time some of you who are familiar with the spectroscopy from the ground in astronomical context, this is the first time from space we are doing multi-slit experiment. Of course, NASA is planning something next year, but this is one we have gone probably before the NASA could take something in space. There are plenty of possibilities of exposures, because these are again observatory class mission with plenty of flexibility in terms of what exposure you want to give, what cadence you want to take. Of course, there will be data telemetry issues and all that. We have to be planning how much the data volume and so on. There is possibility of the spectroscopy. This is again a result from UVCS experiment from again SOHO, which doesn't work for many years. They had single slit. And from there, they could do some polarization brightness, the densities, and the temperatures, and so on. So for the first time, we will have similar possibilities. This is a ground-based facility in Hawaii, Mauna Loa, actually, by higher rigid observatory people. They could measure intensities, Doppler velocities, Doppler width. So there are sporadic observations, and of course, high-quality science from that. But hopefully, from our platform, we will be providing, any number of such observations to get a better. So just this is simulated result of a couple of years back. My student produced that what we will have typically this line profiles and all that. I mean, if you work on spectroscopy, you know what line profile means. It does give you intensity values, velocities. You can take ratios of 2 different lines, get an estimate about the temperature, densities, and so on. So it has plasma diagnostic capability. It's just not, beautiful images alone. So that is what is important. This is again work by Dipankar's group. Dipankar's group produced this magnetic field map. I'm not getting into technical details, but they have some models which predicts this kind of magnetic structures. This was done just before 1 day of the total solar eclipse. There was a famous, American eclipse, and he submitted the paper, I think, a few hours before the eclipse in the archive, just to, make sure that this is been recognized, and it did happen. So as you can see here, there are pretty good match in certain regions. Of course, there are differences also in certain regions. So what is shown here is a white light, corona. What you see, as I indicated in my first say, that typically the corona is dictated by the magnetic field structure. How the magnetic field is evolving, it is taking the plasma also with it. So far, people, and as you can see, there are many more finer structures. What is seen here. We also know that corona is very much multi-thermal. It's not the same plasma is overlapping with each other. So there are a lot of this kind of problems we can do. Soot instrument, as you know, for the sun, we try to do a sort of multi-wavelength covering the temperature. This is the temperature profile in the solar atmosphere. This is the mystery why the corona is so hot. Some of you probably are familiar with this. So people, to address this question, normally people look at different wavelength filter images and try to do some diagnostics. This is the region where normally people have not focused from space. People have mostly focused in these high temperature regions, primarily from UV emissions. So as I indicated, we are going into near UV, as you know. So, near UV temperature is representative of these tens of thousands of Kelvin. It is representation of the chromosphere of the sun. Okay, so this is December 5th, which has happened. I think there is a music, but don't worry on that. Beautifully, the door opened during the cruise phase. As I was saying, we were already on that line, and there were almost a day's observation, and the door was closed as well. So the door was closed after the insertion again, one by one, the instruments were. But it looks nice, they put a camera on the top. Like we didn't know. We didn't know. They put a camera also to look at the Earth, which we didn't know. So there are a lot of things they do in the back end for further things. As you know from the landing thing also, they did quite a few extra tests. Even this hop-up thing or bringing back these things, these are actually very, very important steps for future prospects of Gaganyaan mission. So this is the first light images of the suit. This is a new line, so-called full disk images doesn't exist. There is a mission, small satellite program from NASA, which has done some smaller field of view mosaics. So we are going to run a lot of joint campaigns with that mission. This is the calcium line. We have been looking at solar chromosphere from Kodaikanal Observatory for more than 100 years, 120 years of calcium observations we have. Then again, as I was referring in the beginning, there are two types of variability. One is the short term and the long term. And the long term variability does give you the major impact in terms of the solar radiation and our climate. So one is space climate, which is a very, very long time impact. I did not talk about that Maunder minimum. It was there in that slide, that there was a period in 1600 where almost 40 years there were no such spots recorded. And during that time, Europe was, extremely cold. It's called mini ice age. And now we know, going back to the millennia, different other proxy records and all that, there was 22, 23 such mini ice ages in the past. So I don't think in the modern day we can, afford a mini ice age, not in Kolkata at least. All the monkey caps will come out very soon. So this is the black body spectrum, what you see for the total solar flux. So we are focusing only on this region, 200 to 400 nanometers. But the challenge of building any instruments in this is, you see how many orders of magnitude changes in the flux. So you have one camera, you give an exposure, it has to have a very fantastic dynamic range to really capture the weak flux and the strong flux as well. So I'm just mentioning that these are the challenges why people have not done it with a single camera. Of course, the technology is improving. Thankfully, we got the chip from E2V, and the camera was built at Aryabhatta. Ram and others did that. It has, these kind of different filters. So different filter, which is sensitive to certain temperature line, probes the different atmospheric layers of the sun, primarily up to chromospheric height. And it also impacts, if you look at these, wavelengths, it penetrates to different depths in our atmosphere as well. So this is just a very quickly to highlight that again, our atmospheric science, nobody has actually started looking at soup data. I don't know how many new things I can venture into. We tried our best to influence people in geomagnetism and other institute. Please come and work with this data, because it is really, really unique data. No one has this. And as I indicated, that this depth at different heights and all that has a lot of impact in our ozone formations and so on. So if you do not understand the variability near UV from the sun, you do not understand the impact as well. So I hope, and someday, yeah, we also tried with some colleagues from Pune to pull them in this field. These are again several filtered images from soup. So it's actually quite amazing. We were under the impression after the launch that 6th of January, so nothing is going to happen. But within 10 days or so, people were told that come back to your drawing board, come back to your data pipeline things and so on, because they, we were asked to sort of start doing some tests. So these data is taken almost a month back from now, which has, of course, still a lot of things to be corrected and all that. But we didn't expect that such opportunities will exist. And then, so we call it a verification phase. Was supposed to start from 6th of January after the insertion. It has started almost 2.5 months back for different payloads. Not for all payloads, depending on its complexity and so on. But it has started. Videos, this X-ray spectrometer has already detected some flares. I think some papers are going to come out very soon. And they compared their fluxes with the Bose satellite. These are two NASA satellites in different energy bands. And the match, of course, it still needs certain calibration for the fluxes and all that, because we haven't, really calibrated the instrument, properly. But the timing-wise and the quality of the data-wise, even if I would point out that this looks much smoother, because the cadence, what even Bose has, ARIES has even better. So you will see even more fluctuations and all that. So there are certain things, some other contexts you call QPPs, quasi-periodic pulsations, we see in the sun as well. So it has been recorded from the two X-ray spectrometers already. In situ instruments, very briefly, as I mentioned, aspects here, and these are two components. This is sitting here. It has an ability to look at the 360 degrees almost, because these particles, when they come out of sun, it doesn't actually go through a straight line or radial distance, because there is something called a Parker spiral arm, because sun also rotates and its magnetic field also gets into that kind of spiral structure. So the particles, they form those, they follow those Parker spiral arms. The particles normally gyrate along the magnetic field lines. They cannot penetrate it and so on. So which direction the particles will come, will be recorded by this. And that will be projected back to the sun to really get a 3D view of the Parker spiral arm. So these are theoretical concepts, but nobody is able to really track the particles. So these will have those kind of extra abilities. I was told it was not there earlier. Then there is a boom, and there are two probes to measure the magnetic field of things coming from the sun. Apart from the background thing, also the CMEs which will come. We must point out that the satellite is not magnetically clean, what we call it. So there is not such material which has been used to shield the induced field, because we have a lot of moving parts. So as moving parts means currents. So any currents will induce a field, and that can give you a field which you are measuring from the because of the motion of the either the mirror or the some other motors and so on. So what people are trying is, we have two probes at two different distances away from this, and from the differential measurement, we try to eliminate the influence of the satellite. Of course, there is a clear assumption that the satellite is giving a sort of steady magnetic field and so on. So what you normally expect when a disturbance comes, if a CME like this kind of thing, that CME also has different components. This is called the, magnetic flux rope. Then there is some cavity. Then there is a shock, which is ahead of the magnetic flux rope. And then you see this kind of, fluctuations in different parameters, field, velocities, densities, temperature, and so on. And when you have a more, a regular kind of stream of flows from the sun, there's something called co-interactive regions, because there is the solar wind, which is again asymmetric. There is some places where the wind is slow, some places they have the wind which is fast. So these transitions, there are certain regions where you have transitions from fast to slow. So they're very, very interesting regions. They are dragged, and you have stream of particles which can follow through, and they will provide this kind of series. This is a cartoon diagram, so to say, that when you record a signal and its variability, you have to then try to fit with the model of what it is responsible for. So this is again another movie, if I can play, this is made by ISRO. This is again another
mission to study sun. Begins
some of the recent work from, recent studies from Parker. I will just skip this. What I want to highlight is this is a very important element, multi-viewpoint observation, to have a comprehensive understanding. So I'm not showing you Parker's result, but what I want to highlight, somebody asked question, are we alone in space? These are all heliophysics mission. So these are all heliophysics mission, which is there in space. Some of them are, in the formulation phase, which is highlighted by this yellow thing, like, the Muse, which is expected to launch. It is again a multi-stage experiment in a couple of years. UBST, this is a Japanese mission, and Swarm, and so on. But implementation is already there, and the primary operations are all indicated there. And this is again extended operation. People launch for a few years, but then if you do not find a substitute in space, you get an extended operation. SOHO was launched in '95, and still it is operational, because there are certain instruments which are not there in space. So SOHO has been continuing to observation. So we hope that we'll take a lot of time to do our research, and we'll always keep with ISRO. Please run it for as long as possible. The jokes apart, I think that's also another big advantage of going to Lagrange point, that you expect the lifetime of this mission will be pretty long. So we have gone there already. So we are not alone. So it is important to really work with the community, because to get first is our own mission has a fantastic capability of doing multi-wavelength, and combination of in situ and remote sensing. These are again two different kind of things. Even I tell you, the in situ people, their data formats is different than the remote sensing instruments. So we need to talk to each other to understand, how we can work together. And again, once you include the results from other missions, your credibility, your visibility, everything also goes much better. And SOHO had 13 instruments. We had 7 instruments. There are other, missions which has multiple instruments, which are always complementary. So if you really work together, your results will be much more comprehensive. So that's a thing which I time and again I try to emphasize to the younger generation. ISRO has given ARIES this responsibility of the support cell. AstroSat had a support cell at IUCA, and we are thankful for that. And for younger colleagues, please, join support cells activities. We do regular workshops. In fact, a workshop, next one was scheduled to do in the ITN, but for some reason or other, they couldn't. Probably we will have it here with Madam's support, because Eastern region always gets into a problem because there's so many people, who are interested to participate in this kind of space programs or, other programs of national importance. But we do get all the students from this region and they're working somewhere else. But it is important to train these bright guys here. So we'll be happy to come next. The next one is now being shifted to Jaipur. It's 6th, 7th, and 8th of February, just after the ASI meeting. So please do join us. Again, as I indicated, it's a real lifetime experience. And we are privileged to be born in this time, probably in Indian context as well. And thank you for your attention, because I come from this beautiful place also now with some of my colleagues. Do not know how they are here. So this is taken from very close to our observatory, the mountains. Another, this is a promo. Yeah. So this is a promo. This is a promo. On spare time, if I can manage to get some spare time, I go on stage. So there is a play in Kaput Theatre in 2 days' time, 6:30. So this is a 17th show, I think, of this particular play. And it's quite a demanding task for me, because I try to act a person from this region, which is very, very difficult. We call it Shadna. So I try my best to do that. So our Shadna is there in our professional life with Aditya now. I think that hopefully for next 10 years, we will be all busy with that. And thank you for your attention.
Wonderful talk, and introducing us to this mission.
Yeah, sure. Actually, without the questions, the talk has no meaning.
Yeah.
I have a non-physics question. So the movies that you showed about the sun, are those CGI or optical telescope?
Yeah. So they're not, most of them, of course, most of them what I showed was EUV. They're not optical. So they're taken with CCD cameras, very similar to what you have in your phone these days. And since, when you go to space, only you can see these UV or, near UV or X-rays and so on. So majority of the images which I have shown is in ultraviolet and taken from space platform. So optical telescopes, of course, the ground-based are there.
Color ones?
They're all given artificial color.
Okay.
All the scientific instruments are taken with the black and white, actually. And we put artificial color to just differentiate between one temperature plasma with the other temperature, because we use different filters and some nomenclature is followed. That green means, hotter, or red means slightly cooler. So some kind of, demarcations is done. And this is which is clearly stated normally in the caption.
And is there some CGI also?
Yeah, so depending on the pellets of individual detectors, so they will have a scaling. So because it's not standard, because of the detectors are not always the same.
Nice talk, Dipankar. I was told that any moving part in space mission is a risk. So you have already opened the door once. Why you have closed it again?
Yeah, because you see, we're still traveling, and this during the thruster movement, you have to close it because contamination is a big issue. So this is a near UV instrument. So these doors have possibilities are multiple door operation. So how many doors, how many operations is they have set 500 to 1,000 even. So a lot of redundancies has been kept. And even if you know these are run by command, if one fails, there is a redundancy apparently. Another set of clips are there and all that. So to be honest, ISRO has been doing a lot of things first time because of our demand. You normally they don't do it. Even say slit movements, middle movements, rastering, how fast you can do the raster and come back to the home position and then do it and all that. First time they have developed those. And those motors and all that has been developed in ISRO labs. DSCC has done those motors. And so how many, even for rastering, since you asked this question, for rastering, the spectrograph which are there in Soho, it stopped rastering after 7-8 years. So you can only do it in a sit and stare and so on. So moving parts have these challenges, but ISRO is ready to take up those, which is internationally demanded by good science.
In case of sun, we know that air is the true energy of the air, 40 watts maximum air. But nowadays we are studying that many small stars is giving air about 36, 38. So in such kind of scenario, you find that habitability in the earth like something is ozone disperse.
Since you asked this question, see what Shroman is pointing it out. There are other stars, and now there are big flares of much higher energy has been recorded by a lot of satellites. So we call them super flares. So in the case of the sun, now there is a couple of nature papers. They've tried to predict how many super flares is likely to happen in a sort of 1,000 years period and all that. So there are predictions that super flares can happen, not in year. So that's why the monitoring of these total activity is very, very important. So the moment such big activity and such that. Having said that, there was a Carrington event which happened in 1870 something. So that was that was recorded from India. From India, some from Kulava, there were some records. People did not really have good calibrations and so on, but it is known from historical, records and all that. That was a very, very strong flare. And Carrington kind of flare today will be devastated. It will be, I do not know how many trillions of dollars will be lost. Yeah. I mean, it's your WhatsApp 1 week. Very, very.
Okay, I have a question which sort of you pointed out to me regarding X-ray imaging. So essentially, whatever data we are seeing here, it is multi-dimensional. So there is essentially a back reconstruction model which should be there in the pipeline. So what is the sort of pipeline, data pipelining is there already, and how people could access that? Okay.
There are two parts of your question. One is, see, I tried to connect the physics of it and with the observation what we are seeing. So obviously, what we observe demands a data pipeline to process the data, and that is in a fairly matured stage. I would put it that way, because that tests have been done with the test data. Now the real data comes, so of course the data pipeline will have to mature further depending on the requirements of the noise and all those things as you know. Now in terms of the modeling efforts, so far it has been sort of two independent exercises. So what people have to do it that observational data has to be your boundary condition of the model. That's what Dipankar and all these groups do. They do look at the magnetic field map on the surface of the sun, and then they put that in as the initial boundary condition. So for many such things, though, it's like weather predictions also. Weather predictions is crucially dependent on how often you are able to, how closely you are observing different things, and how often you are observing different parameters. So here also the prediction and all these things, of course, it also depends on how well you understand the physics of it, because it's not very straightforward, simple hydrodynamics. There is magnetic field on the top of that, and that magnetic field has a three-dimensional behavior, which is very different at different parts. But with certain assumptions and certain things, there is some progress in those modeling. There are also semi-empirical formula by looking at statistical properties of these things, which you can connect with the observation number, and some kind of prediction. But we're still not reached the stage of perfection. There's still certain uncertainties which we still have to solve.
Any more questions?
Yeah, just sort of.
No, yeah.
My first question is,
Go ahead.
yeah. So how intricate it is for ISRO to put this Aditya L1 satellite in that Lagrange one point? And second question is, what is the viability of the instrument in terms of prediction of the solar storm and its impact on our Earth magnetosphere, and which indirectly cause the satellite communication disruptions? So I just want to know the merit of this instrument compared to the other NASA satellite which is dedicated, you might know. So just two questions.
So to be honest, there are two questions. First is how complicated it is. Must be very complicated because others have not done it, right? So we are the third in the business. Apart from ESA and NASA, we are the third country in the world. This is something which we have done before the Chinese to reach L1. Incidentally, China tries. There's not much of record what happened to that, but apparently it was a lunar mission, and at the last phase of the lunar mission, they tried to go to Lagrange, and nobody knows what happened. There's no record of that. So obviously that means it is. I mean, of course, everybody knew it is quite difficult. Since you just asked the question, so even in the case of the Mangalyaan, what you needed to get into the gravity of the Mars, right? You go there, you're afterwards slow down in an optimum way so that you get into the gravity. Otherwise, you will miss. That was that time the most challenging thing. But here you think about this Lagrangian point is a singularity point. It's a mathematical singularity point. There's no gravitating object there.
Hello.
The orbit is separate, but at that point there is no mass. So it's a completely on calculation. It's a completely on simulation that in a three-dimensional space you have to calculate the forces, and then you know where exactly it has to be. So the control over the dynamics of the satellite has to be so much sophisticated that really demands a different level. I do know that ISRO has taken help from JPL. So 6 months we have also an understanding with NASA because this calculation also crucially demands continuous monitoring of the satellite position. In fact, I do not know how many of you recall, we were also in quite tension. In the first launch time, also first hour, we did not have telemetry for some 10 minutes. And the telemetry came first was from an Australian island. So ISRO had some other ground support taken from European Space Agency also. So there is some consolidated effort which is necessary. So it is quite. Nothing is very simple in space, as well as I could now see this. Your second question is how much these instruments are going to be scientifically viable and so on. I think it's too early to say that. I think, as I said, काम तो अभी बाकी है, and our job probably starts now. So I think it's our now requirement to prove that credibility. It's your requirement to prove that capability, right? Your generation has to work on the data and show that what it is credible. So I think it is too early to say that big things. बोलना तो आसान होता है, but I think it's too early to comment how it is going to be in an international scenario or comparable to NASA mission or ESA mission. Let's do some science and then comment.
Final question from Akshay.
No, I just forgot what I wanted to ask actually. Let's take upon continue upon the last question. So there are several other missions which have gone to L1 at this stage. We are not alone. So are also there other missions also to L2, or is there any scientific, pros and cons of maybe in terms of futuristic missions of going to L2, and are you people planning on it?
Yeah, we are solar physicists. We don't want to go to L2 because we can't see sun. Because Earth will block. So L2 is most ideal for in long distance, deep sky.
I see.
So that is why the James Webb is there, because it also provides a shadow of the Earth, and that allows them to do the infrared astronomy and so on even more efficient. So L2 is for other astronomy, not for science. Yes. Other Lagrange points are of course very good. There is a location called L5, which is in the side, and L4, which is the other side. And we were almost going to be L5 because Dipankar is also laughing. Because then said, Professor Yuva Rao, after a few years of L1's project and all that, he was very adventurous and he called us and he said, would you like to go to L5? Okay, smart. And that time, when no L5 mission could have been first in the globe. But other condition he put in that you take the same instruments, you have make two and go there. But we said that will be not correct. Because L5 is a perfect vantage point for some specific instrument which we know. It should have a magnetograph, it should have a heliospheric imager and other instruments which L1 Aditya do not have. So you take that, it's like, you have the same glass, but you go into another room where you can't see anything. So it would not have made that impact, and I think international community would have sort of said, they're going to L5, but with the wrong instruments. So we pleaded him that, please let us build some others, other instruments and all that. We actually submitted some proposals also, but then he looked at the proposal and said, hey, these are the same guys. We are going to build this chronograph, we are going to build the heliospheric imager, we are going to do this modeling, and we are going to do this. Please, delivered L1, then we will give you L5. That was Professor Rao's comment, but he's no more. So I do not know when we'll have such opportunity. Meanwhile, now NASA is jointly have approved the L5 mission. So even if we get an approval, we will not be the first. But there are opportunities for the going L4 still open. So, but these are very, very expensive and long distances as well. It's much more complicated than L1 as well.
Yeah, thank you very much. So I'll end with the last question. So is your beard grown for the L1 mission or for this?
It is there from St. Xavier's College time. Yeah. Probably the director thought, I don't have to get much makeup for this guy. So he chose me for the job.
Thank you for this wonderful.
Thank you.